much. Thanks to the organisers for bringing me here. It's, this is definitely up there with Lumini and Banff as my, amongst my best conference destinations. It's a really wonderful place. So this talk is going to be a very concrete talk. But the first 10 minutes is going to be some kind of beautiful nonsense. So it's important that we don't get too bogged down in this, so I'm not going to enter into any very extended discussions, but I just want to give you some kind of big story that what I'm going to talk about fits into, because what I'm talking about is really quite specific. Okay, so this kind of beautiful nonsense. We start with, so it's kind of a big program. So we start with, and I also appreciate that many of these words won't make any sense to people, but just please wake up in 10 minutes when we start getting specific. So we start with something called a CY3 triangulated category. So this is what I spend my time thinking about these days. So the sort of example you might, the basic examples are the bounded derived category of coherent sheaves on some Calabi-Yau threefold, or the Fukaya category. But there are also some simpler examples which come from quivers. You have to choose something called a potential, which you may know about. But anyway, there are some examples of these CY3 categories. And the first game we play with this is we go to something called the space of stability conditions. So this is some complex manifold. So for anyone who's coming late and is terrified, there is no need to understand any of this. It's a big word. Okay, so there is some complex manifold you can associate to this thing. And then the next thing people do is that they define DT invariants, Donaldson-Thomas invariant. Maybe this is the name. This is going to be M throughout the talk. And these things are rational numbers in general. And they depend on a charge. So some class, for us that's some class in the Grundy group of D. And sigma is some stability condition. So sigma is in M. Okay, so somehow once you have chosen a stability condition on this category, you can form moduli spaces of stable objects of some fixed charge, or Chern character, or whatever, and then you can take basically the Euler characteristic of that moduli space, some fancy virtual Euler characteristic, and you get these numbers. Yeah.
So very stupid. D is your category.
D is my category. Yeah, thank you.
Okay.
Thanks. Okay, so this stuff is rigorous so far. There is no problem here. Even for the quintic threefold, due to some work of very clever people like Chunyi Lee, he was able to construct stability conditions on the derived category of the quintic threefold, and the definition of the DT invariance works. And in principle, this is completely rigorous. But of course, there are many things we don't know about. Right. And then there's another arrow, which I would definitely explain, but this board is in the way. And this is going to go to something called a void structure. And this you should think about as being something like a nonlinear Frobenius structure. And of course nobody knows what this thing is, and so the point of the talk really is going to be basically to describe an example of one of these structures. And there is not enough chalk here to draw sufficiently many question marks on this arrow. We don't understand this arrow in any kind of generality. We know how it works in some simple examples. That's it. So this arrow, it has to do with things you may have heard me talk about, these kind of nonlinear Riemann-Hilbert problems. To a first, maybe to physicists, this is very much related to work of Gayato Molonitsky. I think it's also related, often physicists say TBA at this point, but I don't know what that means, but that's some sort of system of integral equations which is more or less the same as this nonlinear Riemann-Hilbert problem. So basically this is the big blockage in this kind of crazy dream I'm describing. But certainly there are some examples where we know how this works. And there is some hope that maybe some weak version of this will get proved soon. And then the last arrow is simpler, but I'm not saying we completely understand this either. Maybe one question mark is enough for this. We get something called we use this structure to define something called a tau function. And it's a function on the total space of the tangent bundle of M, which is always going to be called X here. So this is the total space of the tangent bundle. And the other thing is this is really a section of a line bundle. So locally you can trivialize this line bundle and then you really get a function. And this seems to have something to do with non-perturbative, topological string. So again, this is a very questionable statement. So that's kind of the dream that we're trying to work out in some examples. Okay. I'm going to explain some of how this works in a very simple example. So basically this works. There's two classes of examples when basically we sort of understand this when D is the derived category of coherent sheaves on Y, where Y is some non-compact CY3 without compact divisors. So the basic example, e.g. the resolved conifold. Okay, so that, yeah.
When you say it works, you mean all the arrows work, or?
They maybe don't work completely perfectly, but yeah, certainly we get here, we can state the Riemann-Hilbert problems, we can solve the Riemann-Hilbert problems and show there is a unique solution, and that gives us a joy structure, we sort of understand that pretty well. And then we can think about this tau function, and indeed it is, it has an asymptotic expansion which coincides with the Gromov-Witten generating function. So, yeah, so you could say in that case it works. And the second class of examples where we know this works is, when I put this on, maybe I can even just put it here, is what I call categories of class S A1, because these things are somehow related to the supersymmetric gauge theories of the same name. So let me say something about this. So if I take some genus and I take some collection of pole orders, and I assume that there is at least one pole. I'm not simplistically, let me assume that all these orders are greater than or equal to 3. Then there exists D, some CY3 category, such that if I take the space of stability conditions and I mod out by the discrete group of symmetries, so you think of it as something like a braid group, then this is the space of quadratic differentials of type G, M, where this space, where am I going to fit this in? Okay, here, parameterizes as consisting of C and Q, so C is the curve of G is G, and Q is a meromorphic quadratic differential on C poles of order I and simple zeros.
Is it necessary to require mi equal or greater than 3?
Where I said 3, you mean?
Okay, is it required to be equal or greater than 3?
So if I change this to 2, this statement is not quite true because the space you get is like this, but it parameterizes, basically the zeros are allowed to collide with the double poles. So there is some boundary where the poles become simple. Yeah, so, I mean, there is some analogous statement, but it requires a little bit more care. Okay, so this was some nonsense, and then today we're gonna look at this category, a category of class S, but we're going to take genus equals 0, and n is a single pole of order 7. I didn't tell you what this category is, and I'm glad no one asked because I didn't want to say. But in this case, D is basically associated to the A2 quiver. So it's not, for those of you who know a little bit about this, it's not the derived category of the A2 quiver. That's not a CY3 category. Associated to this, you can construct various categories, and it's this one. But basically, if you're a geometer, you should think of this as being like the Fukaya category, a piece of the Fukaya category of a threefold, where each of these is a sphere, a Lagrangian three-sphere, and they intersect in one vertex. Sorry, they intersect in one point. And somehow, if you took the part of the Fukaya category generated by those spheres, then this is what you would get. So it's like a baby example of a CY3. And the quadratic differentials that were coming up here so these are on quadratic differentials. Okay, so this is a quadratic differential on P1. I take x, just some standard coordinate on P1, and I write this cubic polynomial, and I write dx squared. And what might not be obvious to you is that this has a pole of order 7 at infinity. But if you think about it, I mean, if you write x equals 1 over y or something, and compute this, you will get a fourth order y there, and this will give you 1 over y cubed, so you'll get 1 over y7. So yeah. And this weird labeling of the coefficients will hopefully become clear later. Okay. So that's somehow the end of the kind of general thing. There is some general story. We would love to make it work in bigger examples. For example, for a local P2 or something like that, that would be a big step forward if we could do that. But for now, these are the kind of examples we can do. And already here it's pretty interesting. And so today, oh, my arrow is broken now, but today, yeah.
Yeah, just a question. So here you have two types of examples. We're in the second one, but it should be closely related to the result conifold, right? Is there a connection between the two of them?
Not that I know. I mean, the thing about the resolved conifold is, on this class, is that there's no intersections of branes. So like the Euler, whatever you would call that, like I would call it the relative Euler characteristic between two things, is always zero. In other words, a curve on a threefold doesn't meet another curve. So all intersection numbers are zero, which means that the Riemann-Hilbert problem is basically kind of uncoupled, which makes it quite easy to solve. But so you can solve it by superposition of some basic solutions. Whereas this is not the case here. I'm already here. These two things are intersection number one. So in a way, this is more complicated. Yeah, so today I'm not going to tell you anything about this arrow, really. I'm just going to describe this, the answer you get in this case, because it relates to Painlevé I and things that are very familiar to some people here, but somehow it is a little bit different to the normal story, so maybe it's interesting to discuss it a little bit. Okay. I hope that's clear. So the rest of the talk is going to be extremely concrete. So I'm going to start by talking a little bit about some geometry that you get on spaces of quadratic differentials. But actually, I'm just going to do it in this particular case that's of interest here. So I'm going to take M to be so this is parameterizing those quadratic differentials over there. Two parameters, t and h, and this discriminant locus is where they have simple zeros, so I need to remove that. So that thing is I'll take out that discriminant locus. And then if I take some point in M, of course I get some corresponding quadratic differential like that. And what it gives me is the first thing that we have to think about is this double cover. So there's a 2-to-1 branch cover. And this is really just given by y squared equals x. Okay, so it's the Weierstrass cubic mapping 2-to-1 down to P1. So this I'll probably call the spectral curve, and this is exactly as appeared in Bertrand's talk. And an important thing to know, I'm going to write this in a slightly fancy way, but it's pretty concrete, is that there exists an isomorphism between the tangent space to this parameter space at our point M and the cohomology of this curve. Okay. And so this is an isomorphism. And the way you get this is if you've got some tangent vector in here, here's the fancy way of writing it, you can consider, what do I want to consider, y dx, so that, what is that thing called, the Seiberg-Witten differential, on my spectral curve sigma, and I can take its de Rham cohomology class, so that will actually give me a class in here, and then I differentiate that in the direction w using the Gauss-Manin connection. Okay, so that's the maximally fancy way of saying this. Okay, but let's say this more concretely. I mean, this is basically the statement that there exists local period coordinates on M, which are given by saying, okay, so I take a basis of, let's call this Z, and then these coordinates are just going to be the integrals around these cycles of y dx. Okay, so those are the local coordinates. And the fact that they're local coordinates is basically that statement. Yeah, so there's a couple of so there are several bits of useful information this gives us. So maybe the first one, let's call them A, B, and C. A is that there is a symplectic form. So the kind of the intersection form on gives you a symplectic form. I should say, complex symplectic form on M, on yeah. You see, I mean, a symplectic form is essentially what's the word? It's a skew form on the tangent bundles, tangent space at each point, but we have the intersection form here, which is a skew form. So that just gives me a complex symplectic form. You can easily see that its d omega is 0 because of these, because it's constant in these local periods. So that's one thing we get. The next thing we get is something that they call an integral affine structure. And that comes about because so we have this isomorphism. But inside here we have a lattice. Like the integral cohomology. And so that defines me a lattice in here. And that's what an integral affine structure is, essentially. It's just a kind of, so, this is C2. This is Z2. It's just a kind of integral thing inside your tangent space at every point. And so, I mean, again, in less technical language, this is just the integral span of the d by dz i's. Integral linear combinations of these basic tangent vectors. That's a well-defined thing on this space, so that's an integral affine structure. So you actually always have one of these things on any space of stability conditions. But so I should say that everything I'm saying here works for these spaces quad GM in generality. I'm just doing it in this special case to make it more concrete. Is that? Yeah. I don't know whether I can fit this in. So there's just one last, well, sort of ingredients I need to discuss before I go to the sort of main picture. Which is some kind of, yeah. I mean, the fancy way of saying this again would be an abelian Riemann-Hilbert correspondence, but I mean that is really a bit of a fancy. What am I trying to say here? I'm going to be interested in this quotient. So I have the tangent space at every point of my parameter space, of quad GM if you like, and inside there, that's some kind of c to the n, and inside there I have some z to the n. I can take some the quotient, and I'll just have some c star to the n, and more invariantly this is h1, like this. Now the slightly tricky thing is that it's useful to think of elements of this group as holonomy of line bundles with connection. Okay, so, you know, we're used to the statement, I hope, that kind of representations of the fundamental group into a group G is the same as kind of G bundles with flat connection. So in this case, G is just C star, so, and, you know, maps into C star, instead of maps from pi 1, I can take maps from H1 because C star is an abelian group. Anyway, so this thing I can think of, this is canonically identified with pairs consisting of a line bundle with a connection, holomorphic connection. So L is a degree 0 line bundle on sigma, and this is a holomorphic connection. So this is some kind of Riemann-Hilbert map. You take a line bundle with connection and you think about its monodromy. Now, line bundles with connection, I mean, again, we're used to the statement that the difference between two connections is a one form. So this is nearly the same as a cotangent bundle to sigma. So it's nearly the same so I should say that this is equal to sigma because it's a genus 1 curve in this case. And so it turns, so now I'm saying stuff that's a little bit special to this example, and it turns out that this is actually birational. And this thing, because again sigma is genus 1, the cotangent bundle is trivial, so this is actually equal to sigma plus c. So we get some, I wish I'd done this on a full board. So we're going to get more concrete in a second. This is the last thing I want to say. We're going to want to think about coordinates here, so why not we just take R in there and point QP in here, so where P squared so a point of this spectral curve is indeed exactly a point Q and P satisfying this relation. This is in the complex numbers. On the other hand here, I mean, we can think of an element here as e to the theta 1, e to the theta 2. Since we have our basis somewhere, we have a basis for H1, so we can think about that there. And you might wonder, what is that map explicitly? I mean, I've said that these things are almost the same. And there is a formula for it, which is not super important, but let me just write it. I mean, in fact, that formula is not going to play any role. But just to say that this is a concrete thing somehow. Okay, so so I'm going to move on to to a more concrete picture in a second, but let me just try and summarize what we did here, because it was pretty confusing, I guess. So we were thinking about M, which was very concretely just kind of C2 minus some discriminant locus, and this was an example of one of these spaces of quadratic differentials. So to each point in M, we had a quadratic differential, and whenever you have one of those, you have some spectral curve, which is this double cover. And we discussed the fact that the tangent space to any point in this space of quadratic differentials, you can identify with H1 of the spectral curve. And that gives rise to some local coordinates, and the kind of span of those local coordinates, where did it go? Here. The corresponding integral span of the d by dz i's is a well-defined lattice inside the tangent bundle.
Sorry, could you please explain one more time how you decide about this theta I being in this form?
How do you work that out? Yeah, that's a good question. Not necessarily. So how do you do this? I'm not going to go through the details because this is a little bit tricky, but what you do is you write L, you think about the line bundle L as being functions on sigma, which have, I guess, probably it doesn't matter, no it doesn't matter, a 0 at the point q minus, at this point, and a pole at infinity. So any degree 0 line bundle on an elliptic curve can be written as O of a point minus infinity. Right, so that's how you think about this line bundle. And then how do you write a connection on that thing? So you're going to try and write D, but the trouble is, if you differentiate something which has a pole, did I say a 0? I'm always confused. Oh, this means pole, right? And this means 0. So if I differentiate something with a pole at this point, typically I'll end up with a double pole. Right? If I differentiate 1 over z, I get 1 over z squared. And that's bad. So what I have to do is I have to subtract some one form. And this one form, if you think about it, what it needs to do is it needs to have poles at both of these points with residues plus or minus 1. So with residues plus or minus 1 at q comma minus 2 and infinity. And that may or may not be the case with this. So I always get, there's two things you can do here, which is a little bit confusing. The other thing you could do is you could take one with a pole there. Yeah, so it might be this, or it might be this. Like that. That's the other thing you can do. There's an involution on your spectral curve. You could also consider that. So I think you'll see, I mean, this has obviously a pole at x equals q. It probably has a pole at both of these points. And that p is sort of going to cancel with that y nicely to mean that this has a residue of plus or minus a half, I guess. Yeah, so something like that. You have to think. It's a little bit tricky, but that's basically what you're doing. You're saying that every line bundle is of this form, and then to write a connection on it, you need to think of a one form with residues plus or minus 1. And of course, there are several. This R parameter is adding a holomorphic differential, right? This guy is a holomorphic differential. Of course, you can't uniquely specify this connection. Any line bundle has a whole family of connections. So that's somehow the answer to the question. I'm sorry it's not super clear, but... Yeah.
In higher genus, are you also varying the complex structure on the curve?
Yeah, absolutely, yeah. So hopefully I said here, C is a curve of genus G.
So it's one of the parameters.
Yeah.
And why is it important to have MIs greater or equal than 3?
Yeah, I mean, don't worry about it. I mean, just so that the theorem is true, but no more important reason than that. Yeah, I mean, it's just... Yeah. The way we define the category when one of the MIs is 2, this is not literally the case. You have to allow poles, double poles and zeros to come around.
So for instance, there's no version when there's no poles at all.
There is, yeah. I mean, I should have said that. So Fabian Haydn extended this to the case when d equals 0, right? No poles. And that's much harder, actually. You're not
Harder to define the category, or it's harder to define the category, or
harder to define the category, but it's harder to prove the result because quadratic differentials. I mean, to prove this result, you need to understand the trajectory structure of these quadratic differentials. And when you have a pole in your quadratic differential, the trajectory structure is much simpler because the trajectories tend to fall down the pole. So, I mean, you don't have any recurrent trajectories, for example. So, I mean, trajectory structure of quadratic differentials, which are holomorphic, you know, you can have the irrational foliations, all this kind of stuff. But these guys are actually much simpler.
Do you have a restriction on the genus in this case, when you don't have poles?
I mean, g greater than or equal to 2. Yeah. Okay. Right. So, that's probably section 3. So I'm going to draw the main picture now somehow. And hopefully, probably you didn't need to know all this stuff to understand it, but to understand it perfectly, probably you will. But it's going to be quite explicit. So at the bottom, I'm going to have my space n. If you remember, it's C2, my equivalent locus. And we discussed that there were some coordinates here, and there's some obvious coordinates, or you can take these local period coordinates. Those are the coordinates there. And then I want to consider the total space of the tangent bundle of that thing, except not quite. I mean, so how am I going to draw this? Obviously, it's not actually a box. And so this is going to be x, and this is kind of like the total space of the tangent bundle, except I've modded out by this integral bundle. So instead of a Cn bundle, it's a C star bundle. And so we discussed some coordinates on here. So one set of coordinates would be this. Or you could also take, I guess, and don't worry that there are different numbers of variables there. There's a relation, right? I haven't used orange for a while. So the pictures of the fibers of this map I would draw is like this. Okay, so somehow Q comma P is defining a point of that torus, and R is, so this is supposed to be a picture of T star of C. Okay, and then what we're going to do is, there's an interesting map to something that's called the wild character variety. Rather confusingly curly X, and this map is going to be called F, and it's going to turn into epsilon, and that's where we go C. Okay, so this is the picture we're going to discuss for a bit, and basically this is the joy structure on F, essentially. What I'm not going to explain, unless forced at gunpoint, is what this has to do with the dt invariance of the A2 quiver. But I mean, you know, maybe at some point I will.
This is going to be wild character variety of which group?
SL2.
SL2, okay.
Yeah, probably TGL2. I'm going to write the. Probably it wasn't so good to do that. And what is this map F epsilon? takes the generalized monodromy of nabla, where so now there's going to be a horrible formula, D. So this is on a trivial bundle on P1. And this is going to be some meromorphic, so this is going to be a family. This is a C star. It's a meromorphic connection. And this is going to be X over 2Y. So that's that. Okay, so this looks like, this is maybe a bit scary if you've never seen any of this before at all. This is the linear system that people usually study in connection with Painlevé I, more or less. And when I say more or less, people don't usually put this.
Sorry, is this just the explicit description of what non-abelian Hodge theory does in this case?
Yeah, that's a good question. So the point, so not quite. So
the space X is essentially just open subsets in the space of Higgs bundles, right? That's canonically.
I mean, this is a Higgs bundle, certainly. I think that much we can agree with, right? So it's
I mean, just even when you write the X, originally when you write just tangent space over the integral part, that's kind of, I mean, your quadratic differential is just base of the Hitchens system, right?
no, because C is varying.
Oh, you're varying, yes.
So we're twice the dimension to the story that you're.
Okay, sorry.
Yeah, no, but it's the right thing to think, and it. So, I mean, so where did all this come from? I mean, there is an extension of the usual spectral correspondence. So the usual spectral correspondence would say that if I took a line bundle on sigma, I would get, downstairs, I would get a vector bundle with a Higgs field. Okay, so that's where the interesting part of this formula is coming from. So I've written, I just rubbed it out, but I mean the line bundle.
It's the same phi.
And the same what?
The same phi as
yeah, absolutely. So this is the line bundle sigma, exactly what we were studying before. If I take this line bundle and explicitly work out what the Higgs bundle and what the Higgs bundle is, then this, well, we're on P1, so this can't be anything interesting. Well, actually it could, but generically it's not. I mean, this becomes O of minus 1 plus O of 1, exactly if I take this to be the point at infinity. Something like this. Okay, but generically this is a trivial bundle downstairs, and this Higgs field is that. Okay. Well, the less well-known thing is, what if I have a connection on L? It turns out that generically that induces a connection on E. So, and that's where this is coming from. So somehow there's a kind of trivial connection on here, and yeah, it's a little bit confusing, but somehow as I vary R, which is varying the connection, R was exactly how this connection was varying, then we get different connections down here somehow. So that's where this is coming from somehow.
And this nabla that you construct from the Dell, is it flat as well? Or?
They're all holomorphic connections, so on a curve they have to be flat. Yeah. Well, meromorphic connections.
Does it have some relation with the Higgs field or something like that?
No, I mean the relation is that, I mean, in higher genus the relation is it's on the same bundle, which is kind of non-trivial, but in this case that's nothing. Yeah,
so epsilon is complex number, but eventually is it going to be small or
No, apologies for that. I mean, it's h bar.
Okay, but so...
Yeah, that could also be small, I guess.
How do you think about it? An arbitrary complex number, or you would be interested at some point in the behavior of...
No, I mean, if I was doing WKB analysis, I would want to send epsilon to 0.
Yeah.
No, I mean, for me, epsilon is going to end up being some point in some parameter in a twistor line. I might be interested in epsilon goes to infinity. Okay. And then, where's my rise? Yeah, I'm not explaining everything here. And so what I want to do now is I want to impose f epsilon equals constant. So I want to take a point up here. So I want to take a point on here. Now, if you think about this, this is two-dimensional, this is four-dimensional. I didn't tell you, but this is also two-dimensional. So when I take the inverse image of that, that's kind of two conditions. So what I should find is a surface up here, which actually generically will map one-to-one down here. I don't know about one, yeah, locally one-to-one. So I can do this. So this is just the isomonogram. I've written them down for your delectation. Of course, you don't have to really take much notice of this. The main thing you need to take notice of is that there are two of these. Okay, so why am I saying all this? Just, I want to try to emphasize the difference of when you come from DT theory and you try and work out this example, you get something that looks very like what happens in the Painlevé literature, but it's just a little bit different, and I'm trying to explain what that difference is. And the main difference is, so usually in Painlevé, R equals 0. Okay? So people don't usually put this thing here. And you can sort of see why they wouldn't, because if you look at this, if I just shift P by R, if I just shift P, I can just absorb this R. Okay? So I can just get rid of this R by changing P. Of course, then I will also have to change H because of this relation here. But nonetheless, I can get rid of this R by just changing the other parameters. But if you're interested in doing this somehow for all epsilon, that doesn't make so much sense, because you have to change everything in an epsilon-dependent way, and then that's not, so it doesn't seem quite so obvious to do that.
Top, when you do this shift, you're adding some pole at the zeros of y, right?
Say again.
You're adding some poles at the zeros of y if you do this shift, so it's not that.
Where's this?
So you shift p dx by r dx over 2y, if I'm not wrong.
Yeah. Hang on, I've made a... Yeah, I made a boo-boo here, actually. This is p, in case that...
Okay.
Yeah, sorry. But it's also true that this introduces poles when p equals 0. It's not, but yeah. Okay, so what people usually do is set r equals 0, and that gives you a further relation on this picture. So r equals 0 will cut, setting r equals 0 cuts this, and that will cut this in some slice. So this was a two-dimensional thing, now it becomes one-dimensional, and I can project that down. I get something like that. And then what typically happens, of course, is that now everything is a function of one parameter. So q is a function of time, h is a function of time. Okay, so that's the usual Painlevé story. And as you can see, this kind of different picture is not really very different. I mean, I just sort of shifted p. I don't think anything big has changed. But sort of geometrically, there is a sort of different story now, because what I end up with is a nonlinear connection on this space, because whichever direction I move in downstairs, I can move upstairs and keep the monodromy constant. So you can just see that here. I mean, of course, I can take linear combinations of these, so I could have a d by dt plus some stuff, or a d by dh plus some stuff. So every vector field downstairs lifts to a vector field upstairs, which preserves the monodromy. And that's completely different to the usual story, which is, so you see, if I set r equals 0, okay, all this stuff goes away, which is great. And then this is a reasonable flow, it's the usual Painlevé flow. But this one doesn't work at all, because this will not preserve r equals 0. So you can't have that flow if you're imposing r equals 0. So that's why I wanted to somehow kind of labor all this stuff, just because this is the simplest example, and somehow it's kind of important that the story is very closely related to the usual one, but is kind of strictly different. I think if you actually try and calculate anything here, you won't, it will probably be the same calculation as you already know how to do.
Sorry, I'm slightly confused about the geometry of the whole thing. So you're saying because you're varying your human surface as well, then your space has dimension which is sort of 3 times the dimension of, I don't know, bonus. I mean, it's like...
Four times, I hope. So,
4, why?
So, I mean, if we call k the dimension of, mg, let's call k equals 3g minus 3. Yeah.
Okay.
And let's say there were no poles. Okay, so the Hitchin base would have dimension 3g minus 3.
Yes.
And the Teichmuller space would have dimension 3g minus 3.
Yes.
And I've got them both together, so this has dimension 6g minus 6.
Yes.
So 2k.
Yes.
This will have dimension 4k, because it's the tangent space. Whereas the Hitchin system would again have dimension 2k.
So this is because this is tangent, Tm is the tangent space of the whole thing. When
Yeah, exactly.
Oh, okay.
So it's like a complexification of the story you know. So normally what you would have down here is the Hitchin base on a single curve, and you would take a compact torus vibration.
Yes. Okay. No.
I'm taking double the dimension down here, and I'm taking a C star to the n vibration. So it's like a complexification.
But then your character, right, it has dimension half of that.
Yes.
Yes.
Yeah, so exactly. It's at dimension 2k again. So if I fix a point here, I end up with something that can map 1 to 1 to here.
And then what is the definition of your flows?
Just take the inverse image of a point in the isomonodromy flows. They're just...
I understand that you can take the fibers, but in what sense it's a flow?
Well, these things are just the tangents to the... I'm just writing down the kernel of df.
Yes. Okay.
Thanks for the question. Okay, so I'm not going to finish everything, but that's fine. So I just want to say what you can do with this. For free, you get something, and also it's relevant to Sasha's question, because, I just said that this was a bit like a complexification of the Hitchin system, in that we've sort of doubled the dimension of the base, and we've replaced compact fibers by C star to the ends. Instead of S1 to the end, we've got C star to the end. So everything is like a complexification of the usual Hitchin story. So something that's very nice is that you actually get a complex hyperkähler structure. So that's the other thing that you see in the Hitchin system, you get a hyperkähler structure. Here you also get one of those, but a complex one. So let me just very quickly say how you get that. So So gives a pencil of nonlinear connections on pi on this map. So what does that mean? It just means that if I have a tangent vector down here, I can lift it to a tangent vector up here at any point. And so that's what this isomonodromy connection is giving you. It's giving you nonlinear connections on this map. And that's the sense in which this is a nonlinear version of the Frobenius structure. Because the Frobenius structure has a pencil of linear connections on the tangent bundle. This is like a pencil of nonlinear connections. And we can write them down just abstractly as okay, so don't worry about this. This is just saying that we have some way of lifting tangent vectors from downstairs to tangent vectors upstairs, and we actually have a whole epsilon way of doing them. And you can see just in the form, I mean, this is explicitly that. Okay, so this is kind of h, and this is the 1 over epsilon times v.
So pencil just means that it depends on epsilon.
And the definition of a connection is that if you push it down again, identity. So this is really a way of lifting tangent vectors. And we can see that, like, if we lift, let's say, this tangent vector, that's the only horizontal bit. This is all vertical stuff, right? This is just changing in the fiber directions here. The fiber directions are QP and R. Okay, so when we project back down again, we just get back to here. And so what we end up with here is this is image of H. So we have some way of splitting the tangent space upstairs into 2 copies of the tangent space downstairs. And now what we do is we define I as J, these things. And a metric using the symplectic form. So this gives me a
It's a priori symplectic. I mean,
is that a priori symplectic?
Yes.
Yes, because it's a tangent bundle, but there's a symplectic form downstairs, so the tangent bundle is the same as the cotangent. So it's also a cotangent bundle, so it's symplectic in that way. But this way it gives it several different symplectic structures, which will play a role further on. And so I'm out of time, so I'll just write one more line, which is that, because this looks a little bit trivial, let me just write it here in fact. It's just a statement. Okay, this, of course, so it looks like I wrote a really dumb thing down, but it's not so dumb because, of course, these things are highly complicated subspaces of Tx, so they're spanned by this, you know, like H is spanned by that vector, and V is spanned by that vector and that vector. Okay. So they're complicated. This is a very complicatedly varying decomposition. So of course when I write I, J and K down like this, they're not so trivial. And you know, a complex hyperkähler structure, you're not just allowed to write down I, J and K, there is some conditions about being covariantly, you know, covariantly constant and all this sort of stuff. So the statement is that the fact that these isomonodromy connections are flat and symplectic, it's kind of equivalent to the fact that I, J, and K preserve the metric. It's a complex metric and our covariantly constant associated Levitivity connection. Okay, so that's what it really means to be a complex hyperkähler structure. Okay, so there, and of course that's highly non-trivial somehow, that I mean, it's the usual business, like in Frobenius manifolds. It's quite hard to write down a whole pencil, a whole family, epsilon family of connections which are all flat. I mean, in the Frobenius case, that gives you the WDVV equations. And in this case, if you write it out, it gives something called the Blavatsky equations. So, I guess just the final thing to say is that this looks a bit like a complexification of the Hitchin system, and maybe that's first approximation true, but there is something I believe that physicists call the conformal limit, and this is much, much simpler than the Hitchin system. I mean, if you see my lecture, maybe you don't think so, but I mean, the Hitchin system is highly transcendental. It involves, solving some very, solving the Hitchin equations and so on. This is purely algebraic. So, I mean, this complex hyperkähler structure is actually an algebraic object even, because the isomonodromy connection is algebraic and so on. And you can take me up on that in a second, Sasha.
I mean, I'm confused in what sense the Hitchin system is not algebraic.
Well, I mean, if you write down the metric, it's not an algebraic function of the point.
But if you think about it just as an integrable system on the cotangent bundle to the modular space of G bundles, then it's completely algebraic.
But the integrable system is not giving you the hyperkähler structure, right?
No, the hyperkähler structure.
Yeah, I mean, the hyperkähler structure is a highly, and that's another thing. I just wrote down the hyperkähler structure. I mean, essentially, I just wrote it down for you. It's kind of horrible, but I wrote it down. No one can ever explicitly write down the hyperkähler structure on the Hitchin. So I'm not showing off here. What I'm saying is that this is a far simpler structure. It's much more trivial than the Hitchin thing, but I claim that it's still an interesting structure to consider. And there's this Gauss-Moore-Nitsky story which relates dt invariance to the Hitchin system. I claim there is some simpler story which relates the same dt invariance to this hyperkähler geometry, and it doesn't leave the kind of algebraic world. I'll stop there. Thank you.
Thank you. Questions? Yeah. The pre-image of this F, monodromy map. Can I view it as some complex Lagrangian sum manifold?
So what was it?
Complex Lagrangian sum manifold with respect to some complex symplectic.
Complex symplectic. What did you say? Complex?
No. This 2K dimensional ring thing. Can I view it as a complex Lagrangian sum manifold of Fs with respect to one of the?
Yeah, almost certainly. Let me see. Yes. Yes, that's right. So, because this thing is a symplectic manifold, I pull that symplectic structure back, I get a symplectic structure here, and then this thing obviously is going to be Lagrangian with respect to that symplectic structure. But moreover, whenever you have a hyperkähler structure, you have all these symplectic forms, I, J, and K, and then you can combine them, and so you get a twistor space and so on.
So there will be a generating function for this manifold.
What will be the generating functions?
Let me choose the downward coordinates.
Yeah, okay. Yes. Mm-hmm.
2K amount of downward coordinates, and then there will be a generating function so that I can get the rest half of the coordinates by taking derivatives of the generating function.
Mm-hmm. Yes.
And actually, that seems to be identified with what's called the Hamilton-Jacobi potential when I describe the isomorphism by this Hamilton-Jacobi equation.
Mm-hmm. Yeah. Well, I mean, we should talk. That's also extremely closely related to what the tau function does that I didn't talk about at all.
Another question is that you only allow the higher order singularities in the beginning.
Mm.
But if I want to get, for instance, if I want to study Painlevé I, I have to get the connection with the regular singularities, isn't it?
Yeah, that was maybe just a confusing point that I didn't say very well. The link from stability conditions to these lower order poles is maybe a little bit complicated. But if you just input the space of quadratic differentials with fixed order poles, then we can build this joist structure, no problem. So I mean, in fact, the case that's available on the archive is the case with no poles. So I forget about stability conditions. I just take the space of quadratic differentials, and where I also vary the Riemann surface, but there's no poles, and then you can construct this joist structure and everything. Yeah, so there is no problem for that.
Sorry, kind of if we get back to the nature of epsilon, so you already said it's got to be a non-vanishing complex number, but if in those isomonodromy equations I try to put it equal to either 0 or infinity, would it still make sense? Like if I put 1 over epsilon equals 0, right? Do I get some much easier isomonodromy which would be without phi or not at all? And in the other limit, right, if epsilon is 0, 1 over epsilon is infinite, would it give me some isospectral flow for phi or not necessarily?
Okay, so to answer the second one first, because that is, I understand that one. So if I take epsilon equals infinity, epsilon equals 0, then I can rescale this, there is no problem. So I'm basically just getting V.
Yeah.
And V, I didn't really say it properly, but V is a very simple map. It's, in the other coordinates, it's this thing. It takes a tangent vector downstairs and more conceptually, if we think about the tangent bundle, and I think about vertical tangent directions, of course they are identified with the tangent space downstairs. So there is a canonical map from the tangent space downstairs to the vertical tangent directions upstairs, which is what this is doing, and that's what that vertical map is. So that flow, in other words, is just flowing vertically along the fibers. And the way I like to think about this is that you should make a space Z epsilon where you take X and, basically you take the space of leaves of the image of H epsilon. So the image of H epsilon gives you a half-dimensional integrable distribution inside this thing, and you can you can take the space of leaves of that. And basically, if epsilon is non-zero, you're going to get this as the space of leaves. But when epsilon equals whatever we were just discussing, 0, the space of leaves is just n, because you're just, the leaves are just the vertical thing. So when you take the space of leaves, it's just downstairs here. And these things fit together to make some twistor space, and what we've just been discussing is that Z0 is M and Z epsilon is X for epsilon in C star. And your other question was what happens when epsilon equals infinity, and that
Does the formulas still look quite, substantial? You just drop one term in each of the vector fields. Is it still even though one feels if one drops phi?
No, I think there's some subtlety here, basically, that you can take the epsilon equals infinity limit of these flows, of course, just by killing these two terms. But that is not the isomonodromy you get by killing the epsilon. So, just forget the Higgs field. The isomonodromy for this is not given by that.
Okay.
And that's something I don't understand too well.
Yes, visibly, probably it's not, right? That looks, formulas still look a bit too complicated to be, but okay, I don't know.
Yeah, absolutely. So that's some kind of slight mystery here. As a result, I don't really understand this twistor fiber at infinity. That's why I was asking about the limit as epsilon goes to infinity of this the monodromy map for this thing. But so that's a question we don't really understand too well.
Is there a chance for this to make sense in higher rank?
I made a promise to myself some time ago that I was never going to think about higher rank. But of course, yes, one should think about higher rank.
Is that what Stemmetic uses? This four Goncharo spaces for that, right?
Yeah. Actually, no, there is a sensible answer to your question as well, which is I mean, what we did here is we took the hitch in base and we doubled the dimension by allowing the curve to bend. Now, if you take a higher hitch in base, how do you double the dimension?
That's what Fog-Gonchar do.
And that's the question of higher Teichmuller theory.
Well, that's precisely what Fog-Gonchar are doing in some way.
What on the coordinates?
Well, I mean, that kind of.
I mean, of course, we know how to do this in higher rank. The higher rank wild character variety.
Sure, yeah,
I mean,
that's-
I don't, but Fock and Gontrov certainly know how to do that. But I think there is a genuine question here. How do you extend the deformations of the curve?
No, I think they do have a definition of high Teichmuller space. What they don't have, they don't have an analog of modular space of curves. They only have analog of Teichmuller space. Mm-hmm. So just of the cover, so they don't know how to sort of, they don't have an analog of mapping class group.
Yeah, I don't even know this though. But I guess time.
I guess, yeah, we should go for coffee. So let's thank Tom again.